In this video, I'll be solving problem 10.6 from Taylor's Classical Mechanics. Part A asks us to find the center of mass of a uniform hemispherical shell of inner and outer radii A and B and mass m positioned as in problem 10.5, which I've drawn below. And it asks us to use the result of problem 10.4, which is written there. It's simply the integral of a function of position over volume expressed in spherical coordinates. We can see that the hemispherical shell is symmetrical in the x and y directions. So we'll say that the center of mass in x equals 0 and the center of mass in y equals 0. Now, what about in z? So the center of mass in z is simply 1 over m times the integral of the density times z, which in spherical coordinates is r cosine theta, dv. So let's find the density first so we can use it later. Density is mass over volume. And in this case, the easiest way to think of the volume of the spherical shell is that it's a hemisphere of the outer radius b minus a hemisphere of the inner radius a. So we'll say that that is m over 2/3 pi b squared minus a squared. Okay. Continuing on, we will now solve this integral in spherical coordinates. So we'll have rho over m. I'm just pulling out the rho. R squared dr sine theta d theta d phi times the function of position, which is r cosine theta. And our limits of integration in this case will be phi, which is in the xy plane, just all the way around from 0 to 2 pi. Theta will be from 0 to pi over 2. And r will be from the inner radius a to the outer radius b. Let's first pull out the integral of d phi, which is just phi, so that'll be 2 pi. Let's put it out front with the constants. Rho over m, integral from a to b of r squared dr. Then we'll have the integral in here of, let's actually move the r's together. So then we'll have r cubed dr. And then we'll have sine theta, cosine theta, d theta. Just like in problem 10.5, we can solve the integral of sine theta, cosine theta with use substitution, and we'll just have a result of sine squared theta over 2. And then we're integrating that from 0 to 2 pi. Pi over 2, which is equal to 1/2 minus 0 equals 1/2. So that's just another constant we can pull out in front. So we'll have m over 2 here. And then we're just integrating r cubed dr from a to b. So then we'll have 2 pi rho over 2m times, it'll be r to the 4th over 4, so let's do 1/4, and then we'll have b to the 4th minus a to the 4th. Let's plug the value for rho back in, so we'll have 2 pi m over 2/3 pi, we've got the 2m from right here, then we've got b squared minus a squared, those should be cubes, times 1/4 b to the 4th minus a to the 4th. So if we do some canceling, we'll have, again, constant factor of 3/8, like in problem 10.5, but it'll be times b to the 4th minus a to the 4th over b cubed minus a cubed. Now, part B of this problem asks, what becomes of your answer when a equals 0? And part C asks, what if b approaches a? So, if a is 0, our result for the center of mass is 3/8 b to the 4th over b cubed, which is just 3/8 b, in agreement with the result of problem 10.5. Now, what if b approaches a? We'll take the limit as b approaches a of the center of mass, which is 3/8 b to the 4th minus a to the 4th over b cubed minus a cubed. If we just plug in a for b, obviously the limit will be 0 over 0, which is unacceptable. So instead we'll use L'Hopital's rule and take the derivative of the numerator and the denominator. So we'll pull the constant out front, and then this is the derivative with respect to b. So the derivative with respect to b of b to the fourth minus a to the fourth is 4b cubed, and the derivative with respect to b of b cubed minus a cubed is 3b squared. Here we have a limit which is 3/8 times 4/3 b, and when b is a, it'll be 1/2 a.